Hello ladies and gentlemen, my name's Grant Douglas. I'm a research scientist with CSIRO in Australia, and what I'd like to talk about today is the development and application of modified clays for the removal of phosphorus from aquatic systems, and talk a little bit about the past, present and future. So firstly, the presentation will cover three aspects of phosphorus management in aquatic systems. I'll talk a little bit about the soils as a source of phosphorus and how we might deal with those. Also talk about the eutrophic input waters, all those of phosphorus, but then also eutrophic systems as a sink, but as we all know, as a recyclable sink effectively in those aquatic systems such as lakes and the like. Okay, in terms of P removal and inactivation, I thought I'd just give a little bit of a background of my research over the past 20 years, and that's really focused on three aspects: to limit terrestrial P movement at soil, mineral-based soil amendments, to remove phosphorus from eutrophic inputs, and again, mineral byproducts used in columns and as wetland amendments, and then finally, P inactivation in eutrophic systems, phoslock and hybrid nanoclays. Now, I won't talk about too much because I think that's going to be covered by a number of the other speakers in this e-conference. I also won't really talk too much about other research other than to say there are other phosphorus absorbents out there that are being looked at, things like aluminium substituted zeolites, calcined magnesia, and also hydrotalcites. Okay, in terms of the research and development of phosphorus absorptive materials, I'd just like to make a few key points at the start. In this area, all research should really be underpinned by a number of points. Firstly, a sound geochemical and mechanistic understanding, extensive laboratory trials, geochemical modelling, upscaling to pilot and or field trials, and also importantly, performance validation of those materials. Also, there should be source material characterizations, so things like major and trace elements. Are there any toxic elements potentially in some of those materials? The mineralogy, to give us an understanding of how those materials might actually behave, any inherent radioactivity, but then also look up these materials are made or synthesized at the leachability aspects, the ecotoxicity that might limit any environmental applications, and also the stability of those materials after they've actually absorbed phosphorus. Now, all of those above forms a basis for an informed and appropriate full-scale trials or applications. And in particular, we want to look at whether these particular materials in mind are fit for purpose. For instance, whether they're able to be used only in fresh but not in saline waters. All of this characterisation work as well forms a basis for eventual long approval with government authorities, as I think we all know is an important step in the process of actually applying materials to the wider environment. Another important point, which is, in my experience, somewhat overlooked, is a long-term commitment to well-conceived short and longer-term monitoring of material performance and ecosystem effects. And finally, all of the above really develops a holistic understanding and engenders confidence in clients and end users. And the important thing here, we cannot afford to have shortcuts. Okay, talking firstly about P inactivation in soils to potentially affected systems, looked widely at mineral-based or mining byproducts of soil amendments. Now, the first one I'll talk about is NUA, which is a titanium processing industry byproduct. Now, in this particular case, we added as a 5% biomass amendment in the top 15 centimetres of soils on a turf farm. And this is a 4-year trial where we were able to see a 97% reduction in P and 82% reduction in N leaching to the shallow groundwater. So really some major reductions in nutrients. And you can see from those graphs we have control in the orange, and these are concentrations of phosphorus in the shallow leachate, and the amendment, you can see the sort of change that the amendment confers in terms of phosphorus leaching. Now if we have a look at phosphorus removal in eutrophic input, and we looked at mineral-based mining byproducts as filtration media. Now we looked at those mineral byproducts on their own, but also in various combinations. And I have a table below that looks at a range of mineral-based mining byproducts, the steel processing byproducts, slags, the NUA, which I mentioned before, red sand from the alumina industry, calcined magnesia, and again, calcined magnesia and red sand with NUA. And those numbers in red are where we see from column trials greater than 50% removal of either DOC, DON, total nitrogen, dissolved phosphate as PO4P, or total phosphorus. Now we used a particularly difficult water here. This is Ellenbrook, local to me, which contains both substantial DOC, often up to 50 milligrams per litre, and you can see that really colour there, but also can be substantially phosphorus enriched, often containing over 1 milligram per litre of phosphorus. So what we can see is that sometimes materials on their own, such as NUA, are very effective there at removing 96% of the dissolved and total phosphorus. But then we can combine NUA with particular material. We look at the last couple of lines there. NUA and calcined magnesia in particular is very effective at removing both dissolved organic carbon and dissolved organic nitrogen, in addition to total nitrogen and phosphorus. Now what this means, and it really opens up an option for us of tailoring the use of either byproducts singly or in combination to actually address the nutrient profile of particular ones, or alternatively to look at giving us the required output. Now, some of these materials in particular, the steel byproduct, as it readily comes to mind, leach a substantial amount of silicon, and that can be important where we want to both reduce nitrogen and phosphorus, but also add silica back where we perhaps want to see or promote the growth of less problematic algal blooms such as diatoms. So let's have a look at those mining byproducts when used as filtration media do to nutrients in terms of nutrient limitation here. So I've got here now 3 nutrient limitation diagrams. On the top left, a nitrogen one, top right, phosphorus, and the bottom right, silica. So where you see the minus N, the minus P, or the minus SI, they are actually quadrants where we see potential nitrogen, phosphorus, or silicon limitation. So if we look at the first example, and black circles, we have and Bassendean sand, the actual soil that the Ellenbrook water flows through. So I treat those as the inputs. And then we have the 3 types of effluents using NUA and the steel, or NUA and calcined magnesia actually as the column media. What you can see is after the Ellenbrook water flows through this column media packed with Bassendean sand, we see a major change away from potential nitrogen limitation. We look at the top right-hand diagram, we see a major change back towards strong potential phosphorus limitation, and in the bottom one, a move away from potential silicon limitation. So overarching all of that is that we actually saw a 99% phosphorus reduction as well. So as well as changing the potential nutrient limitation in these systems by filtering the Ellenbrook water through a column containing also the Bassendean sand, we've seen a change from potential nitrogen to phosphorus limitation and a change away from silica limitation. And this is very important. So we've lowered the concentrations of nutrients by orders of magnitude, but then we've introduced silica, and that really sets us up from going from what was probably going to be a blue-green dominated system to something that may have initially or firstly much less biomass, but also importantly predisposes it to diatom bloom formation if any blooms are going to occur at all. Right, I'm going to talk now in quite detailed fashion about P inactivation. And in a new modified clay that I've developed over the last couple of years. Now, what I've termed this as is a clay hydrotalcite nanohybrid. This nanohybrid clay has a substantial P uptake, around about 4 P by mass when the production of it is optimised. So very, very high phosphorus uptake capacity. In fact, substantially higher than virtually any other material that I'm aware of. Importantly, it can be used in both fresh and saline water, and it also may be used to remove dissolved phosphorus from sewage effluents, which is one of the most difficult matrices actually to address. There's also a prospect for using this nanohybrid clay as a soil amendment, as a riparian zone amendment, and also as a wetland amendment. Range of potential applications quite apart from in-lake or in-system P inactivation. So $64,000 question, what are hydrotalcites? Well, hydrotalcites are a 2+3+ metal subclass of what's known as anionic clays. They occur both naturally, though generally in trace amounts in the environment, but importantly, it's reasonably easy to synthetically produce them. The structure, as you can see on the right, is positively charged metal hydroxide layers, those layers of the purple and the pink there, like hexagons, and also between those layers are the anions, those green golf balls, and also waters of hydration. So those varieties such as H2PO4- and HPO42- are amongst the most favoured anions that can be exchanged into these hydrotalcites. That's a really important point. So how do we make these hydrotalcites or hybrid nanoclays? Well, firstly, we use suitable low-cost feedstock, and then we chemically modify those clays. Preferably, though it's not absolutely important, but we use a clay that contains abundant magnesium and aluminium, but for various reasons we particularly high iron concentrations. We acid leach those clays. We tend to liberate at least part of the magnesium and aluminium, which is important in the formation of the hydrotalcites, but we also often liberate substantial silica. Now that's important because that can actually partition into these hydrotalcites and reduce the subsequent ion exchange capacity for phosphate. During the manufacturing process, we augment these clays with additional reagents, and we also complex out iron and silica, and they're key steps to actually making a high anion exchange or high phosphorus capacity hybrid nanoclay. We also carefully neutralise the nanoclay, which is very important, precipitation of the hydrotalcite. Importantly, one of the reasons we also use clay is that those remnant clay layers actually act as a substrate for the hydrotalcite nucleations. This is where the concept of a hybrid nanoclay came from, that we actually use a clay and then we precipitate the hydrotalcite. The actual remnant clays are also important because they add particle size and density, so that assists where we want to actually see set of these hybrid nanoclays in an aquatic system. We age a suspension of these hybrid nanoclays that we can apply directly to aquatic systems, but we can also apply it as a powder or form pellets as required for a particular application. An image there in the bottom right, you can actually see those hydrotalcite layers that I talked about in an earlier slide. So you can see the individual layers there. Between them is where the anions exchange into, and they often aggregate, as you can see there. So individual platelets of those hydrotalcites and clays actually aggregate into substantially larger particles. Talk a little bit now about the hydrotalcite or HT in terms of phosphate and carbonate speciation. Within the hydrotalcite, there is a strong gradient in anion selectivity or exchange into those interlayers. Carbonate, much greater than HPO42, but also greater than HCO3, but also then very, very much greater than a lot of the common anions that you see in natural waters, the sulfate, nitrate, chloride, and the like. But pH is also important because that determines whether we have carbonate or bicarbonate relative to H2PO4 and HPO4. And so effectively, look at the graphs on the right there. There really is often a sweet spot for phosphorus uptake. In general, about natural waters occur in that pH interval from around about 7 to about 8.5. In practice, though, there's actually a wider operational pH range, as you'll see in a moment. But where we occur well outside that pH range, we may actually have to increase the application rate or adjust the pH in that particular aquatic system. If we look now at examples of phosphorus uptake by the hybrid nanoclay in waters, the sample matrix, I've used waters from the Swan River in Western Australia near to me, which is both an estuarine and freshwater river. We have used coastal seawater, and we've used a range of lakes and ponds. As you can see there from the diagram, we have a range of both pH and salinity. We also had a range of DOC concentrations from about 0 to 50 milligrams per litre. And we also had a range of P concentrations, and that's reflected by the size of those green dots there. So anything from about 20 to 300 micrograms per litre. Now, if we P uptake from those natural waters, well, the first thing to note there is there is a strong relationship between the P uptake and the salinity, the EC there. But we can get P uptake between about 30% at the very lowest at very, very high EC waters, up to about 50 to 70% in fresh waters. Now, what we actually did here was we only applied stoichiometric quantities of this nanoclay, so only the amount in theory required to take up the total amount of phosphate in that waters. In practice, there are competitive effects as well with carbonate and bicarbonate. So in fact, we may actually have to add slightly more of that clay. But nonetheless, given we have a 4% uptake capacity, we only often have to add very small increments to increase our P removal rate up into the 80, 90, 100% range. What I also want to talk about just for a moment is the P uptake of these hybrid nanoclays in sewage effluents. Sewage effluents are really, really difficult. They contain huge amounts of water, they contain particulates, they contain various forms of P from individual orthophosphate through to polyphosphates. So they really are a very difficult target to attack. Here we used a range of sewage effluent, looked at a range of sewage effluent, 3 states in Australia. And as I've said there, complex matrix, often low to high suspended particulate matter, so both particles and colloids, and I also allude to high DOC. In this particular case, we adjusted pH to about 8 from the original pH range varying between about 7.2 to 7.6. Regional range in terms of salinity, or EC, so over an order of magnitude there from about 680,800 microsiemens per centimetre. We also had a large range of P concentrations, again from 1 to up to 270 milligrams per litre, so far higher than you'll ever see in the natural water. But really what I want to highlight here is the exceptional potential of these hybrid nanoclays to uptake P from aquatic environments, and in this case a very complex aquatic environment. So what I've got plotted here on the right-hand diagram was the water removal rates, but then you can see in red the removal rates from sewage effluent, and actually quite surprisingly we get generally between 94 there and 99% uptake from a really, really complex high phosphorus environment that is a sewage effluent. And that's despite that, yes, it being a much more complex or much more challenging matrice. In fact, in this case, we used about 1.5 times the stoichiometric requirement but nonetheless you can see really encouraging results in terms of phosphorus uptake from what is, as I said, a very challenging environment. So in terms of the hybrid nanoclay, I'd just like to outline some of the future research and upscaling challenges that we face. We continue with further laboratory evaluation and performance testing on a range of waters. We've just begun scale up to pre-commercial quantities. In fact, we're going to commence making ton quantities of this material within the next month or so. One of the is to test stability, but also if we go to larger scale aquatic system testing, is to also examine the ecotoxicity of these materials. But based on their chemistry, it's likely that they're probably inherently low ecotoxicity. As I said, we want to move to field trials. Possibilities, and I'm looking to do some field trials in Europe in 2014. Given the encouraging results we saw with sewage treatment plant effluents, we're also undertaking some additional trials with the Australian Water Recycling Centre of Excellence. And we're also looking at options whether to make this clay widely available, partner with other institutions, or perhaps also commercialise. Just to put this new hybrid nanoclay in context, assuming a 2% P-uptake, but as I alluded to earlier, we might even have up to 4% when an ideal clay is used. The clay hydrotalcite nanohybrid is around about, it costs about $1,000 Australian a tonne in terms of raw materials. So that means if we had about a 2% uptake, which costs about $50 per kilo of P, but we also obviously have to include in that manufacturing, transport and application. But what I'd also like to say is that I'm very happy to work with other international researchers to actually further the understanding of this hybrid nanoclay, given its promise up until now. In terms of my P-absorptive last 20 or so years, if you want more information, I'm very happy to send you any of the papers on the range of studies that have been undertaken. And in summary, very important that we have a whole system integrated approach, as I alluded to earlier. So we want to try and manage P leaching from catchment soils. We also want P removal from eutrophic water inputs, but then we also adopt new and innovative in-lake treatments to manage phosphorus that is already contained within these systems. Mineral-based absorbents are now available, or new mineral-based absorbents are now available, and in addition to new P-absorptive clays, hybrid clay that's currently being developed. The important thing to also say is, in this development, there have been shortcuts. As Brian Spears said, no silver bullets are available in terms of from aquatic systems. And with that, I'd like to thank you for your time, and hope to talk with you later about P-absorbent materials. Thank you very much.